Sir, you are audible, sir.
Okay, so I'm sharing my screen. So hello everyone. So I'll be giving my talk will be specifically on the how speech synthesis models have evolved from the conversational to generative AI based. So initially I'll start with the introduction of speech synthesis, then background and literature, some issues and challenges, and then GAN-based speech-to-speech synthesis, and then some recent advancement in speech synthesis, specifically on TTS, singing voice synthesis, then human-computer interface for speech synthesis. So as you can see over here, the figure one, the schematic over the human speech production mechanism. So left hand side is the source filter model. So as we all are aware of the fact that when we talk, we try to make any conversation or we want to convey our message to the outer world. So initially the first part is the lungs. So our air the flows through the oral cavity and the nasal cavity, and based on the this place of articulation and manner of articulation, different phonemes are being made, and these phonemes are the basic building block of any sentence we utter or any message we construct. Now when we make any message by our lips or based on this our on oral and nasal cavity. So the initial part is the message formulation. Then right hand side image that you can see that first one is the message formulation, and then is the language code that we select to convey our message. Then the neuromuscular actions, and based on this neuromuscular action, we make different place of articulation or manner of articulation, and different acoustic waves are even made, and then the listener can understand what we have uttered, what is the content of the message, and this comes is under the speech recognition state. But I am mainly focusing the speech generation part. So as it can be seen that the speech generation can be expressed mathematically in a time domain, like a convolution operation between the glottal impulse and the response of our vocal tract. Then let me go to the categorization of speech in this process. So as of now, we have gone through how we make speech, a human makes speech. Now it is how AI models or machines make speech or generate speech. Now the speech synthesis can be categorized mainly on two types. One is a speech-to-speech synthesis and the text-to-speech synthesis. As the name itself indicates, that in speech-to-speech synthesis, the input is a speech, audible speech, and the output is also an audible speech. Whereas in case of text-to-speech, the input is the textual transcript, and the output you get the audible speech. Now TTS parts have already been is covered by earlier speakers, so that's why I'm giving more focus to the speech to speech in this part. However, in my later slide, I have also included the TTS part specifically for diffusion models. So voice conversion is a specific type of speech to speech synthesis process. So as you can see in the figure 3, the schematic overview of the voice conversion process, we have a source speaker and we have a target speaker. Now the source speaker can be of, I mean, both source and target speaker can be of different or maybe on same gender, or similarly they can belong to same linguistic identity or maybe different. So here in this diagram, you can see that the source speaker is a male speaker and uttering the content hello in English. And the target speaker is a female speaker and uttering Subharam in Hindi. Now, the basic objective of the voice conversion model, which is a speech-to-speech model, is to extract the vocal features of source and target, and specifically the content of the source speaker. Now, what it will do, once it will learn the vocal feature representation or the distribution of the features, then it will superimpose the vocal features of the target speaker over the content of the source speaker, that is hello, and it will generate the hello content in target speaker's voice in the inference stage, such that it seems like the target speaker itself is uttering the content of the source speaker. So sometimes we also call it a deepfake speech generation or artificial speech generation. So it is kind of a style transfer task where we transfer the vocal characteristics of the target speaker over the content of the source speaker. Now, how we can do this? So it follows a three-stage pipeline. Though the first one is the speech feature analysis stage, then the speech feature mapping and the reconstruction. So as I have already explained that in the speech feature analysis phase, we extract the vocal features from both source and target speaker. Then in the speech feature mapping stage, we try to map the source speaker vocal feature. So G is the function, the mapping function, and X is the vocal features that we have extracted in the first stage of speech feature analysis. Then given X as an input to the mapping model or mapping function, it try to map the features to the target domain, that is Y, and it generates Y hat, the intermediate representation. Once we obtain the best representation or the best target features, which is very similar to that of the Y domain, then those features we give to a speech reconstruction model, which is basically a vocoder, either statistical or neural. Then we can get the audible speech, the T hat. Now it follows, the three-stage mechanism we carry out following two steps. One is the training and the inference stage. So as you can see over here, in the training phase, we train the model. There is function G. After it get trained, in the conversion phase, the inference phase, given the new content of the source speaker speech, we can get the similar content, but in target speaker vocal features. Now this speech synthesis process, or specifically voice conversion, can be carried out in following different algorithms. The statistical voice conversion model mostly includes like Gaussian mixture model, phonetic posterogram, vector quantization, etc. And the deep learning models like GAN, VAE, and nowadays people are using the diffusion. And then there comes different types of voice conversion. And based on different types of voice conversion, there are different challenges associated to each of these types. So I will discuss each of these types in my upcoming later slides. The first one is a parallel and non-parallel. As the name indicates, in a parallel voice conversion, we have the parallel content uttered by the speakers, both source and target. Then we do some time alignment. Using DTW mostly we use. So once we aligned, then we started training the model. The model get trained based on the aligned data for both source and target. And then, as I've already mentioned in the last slide, that so we extract the vocal features, then train the model. And once it is getting trained, then the conversion phase, given the new content, we can simply generate. Whereas in non-parallel VC, the contents are dissimilar. Now the question is, the non-parallel can be of unilingual or multilingual or cross-lingual. So in the right-hand side, you can see that the monolingual and cross-lingual VC. So monolingual, as the name also indicates, that it will be from different. It will be from same linguistic content. Whereas for cross-lingual VC, it will be from a different linguistic content. So non-parallel is also, it can be monolingual or maybe cross-lingual. Now the challenges of cross-lingual is like, as because in cross-lingual voice conversion deals with different phonetic contents, different linguistic contents, and as well as different accents. So it makes the process quite difficult as compared to the earlier explained models, because we have to extract some accents, some phonemes, maybe which is not present in the target domain. Then we have to use the concept of mapping, such that even if the model does not have very thin phonemes from target domain, it can estimate what could be the approximated accent of the target speaker. So this is one of the challenges of cross-lingual VC. Now there are publicly available data sets, mostly we obtained from the voice conversion challenges. So the first voice conversion challenge took place in 2016. from where we can get the parallel speech data. Then we have the VCC 2018 and VCTK data. So it's for non-parallel. However, based on the selection of the speakers, we can also take it as we can make it a parallel settings. Similarly, for cross-lingual VC, we have the VC 2020 dataset. So the number 2020 is basically the year when voice conversion challenge took place. So you have like English, Finnish, German, and Mandarin. VC 2020 includes these languages. Then comes the intergender and intragender voice conversion. As the name indicates that in one case we have different genders and another case we have same gender. Now the gender also plays a very significant role because we know that based on the gender as well as based on the age group, the specifically the frequency component gets changes. Now when we deals with the same gender, the intergender VC, it is quite easier as compared to the intergender VC because frequency components get changes. Then comes a very significant type of voice conversion, it's called many-to-many voice conversion. As of now, all the models that I've explained, all the type of voice conversion I've explained is for one-to-one voice conversion. We have one speaker in a source and one speaker in a target domain. Now, many-to-many voice conversion, we can have multiple source speaker, multiple target speaker. Now, it becomes more challenging when each of the speaker belonging to source domain and target domain have different linguistic contents, may have different genders or age group or accents. Then the problem becomes more difficult and the challenges also becomes but more problematic, and then we have to incorporate different types of feature extraction method by which we can extract different linguistic content related information, accent related information, even pitch related information, prosody related information, etc. And then we map the model for many-to-many mapping mechanism or many-to-many setting, where you have the multiple source in one hand, in the left hand side, the source domain, and in the target domain, you have the multiple target features. And then once the model gets trained, in the conversion phase, we also have to specify in which target speaker vocal feature we want. Earlier, it was not same because we know that the model has been trained for one specific source speaker and specific target speaker. But when the model gets trained for multiple source and multiple target, then in the inference space, we have to specify, given the source speaker speech feature, in which target speaker vocal feature we want the generated samples. Then there is another type of voice conversion called emotional voice conversion. So in case of emotional voice conversion, the identity of the speaker remains same. We only deals with the emotional content. Like we have the emotional speech data. These are all publicly available data. So it deals with this 5 emotional informations associated with the different contents. Then there is another type of voice conversion is called dysarthria to normal voice conversion, or some pathological speech to normal voice conversion. So there I have shown one specific diagram that you see in the figure number 12, that we have for the parallel corpus, for parallel utterance or same speech uttered by one dysarthric speaker and one normal speaker. Now we want the model to understand for the same content what was the format information, which usually some distortion in the format information of the dysarthric speaker or maybe any other pathological speech. We want the model what could be the actual format information in the target domain. So once the model understands that for a given content, fixed content, this was the distorted representation, and in the target domain, this was the correct representation, then the model tried to understand how to make changes to the format information of the distorted one such that it sounds like, once it gets generated, it sounds like, or it can perfectly replicate the exact content. Now it has some limitation, like this specific setting is only trained for parallel conversion. So we want the model to learn for the same content what is the distorted male spectrogram, what is the actual male spectrogram. But for non-parallel, exactly this setting may not work. Anyways, so in the later slides, I will discuss rest of the other types. Sorry. So this is another type of okay. So I mentioned I didn't mention. Okay, so easy call data set is one of the data set we mostly use for this is diatheia to normal voice conversion. Then comes the singing voice conversion. So singing voice conversion extension of the normal voice conversion, where we have so one speaker, I mean two speaker, one is source and target, or maybe multiple similarly. But this time we have a singing content. We have the lyrics, and lyrics is not uttered by in a normal procedure or melody. It replicate the melody of some given notes. Now we want the target speaker should acquired or should replicate the same notes information as sung by the some source speaker. So this is one type of or extension of the normal voice conversion. Now we are dealing with in case of singing voice conversion or singing voice synthesis, we deals with melody. I mean the notes gets associated, not only the textual transcription, not only the normal vocal feature, also the pitch information, the melody or the note information also plays a very significant role in this specific setting or this specific type of voice conversion. And this is one of the publicly available datasets. So I have also summarized all the datasets over here, such that once I'll share the slide, it will be very easy to understand the get a summarization of the whole datasets. And then comes the evaluation method. So mostly we are dependent on mean opinion scores, because when we generate something, specifically audio rated data, we want the subjects, the human volunteers, to hear the sounds and evaluate our samples based on their perception. Now this perception changes based on the subject as well. Say for example, we have generated some audio data for Hindi content. Now the subjects to whom have shown the samples and they have to evaluate, they are not aware of the content of the Hindi data. Maybe they belong to some other linguistic group or entity. So in that case, they will be more reliable, or they will be more dependent on only the vocal feature similarity, not the content. So although you use the mean opinion score, but these are the problems we also have to deal with. That's why we also have the objective evaluation matrices. This helps us to understand the vocal, the different features. I mean, to evaluate the generated sample from the aspect of different features. So male substrate distortion, modulation spectra, F-note RMSE, these are one of the very prominently used objective evaluation matrices to understand the vocal feature similarity of the generated sample as with respect to the target one. And there are some other evaluation matrices like the spectral loss and the F-note RMSE I've just shown you. You can see the fundamental frequency, how it is changing. That is called the melody. So fundamental frequency is the prominent frequency component, particularly in time instance t. And if we connect all those frequency and we found a curve, this represents the melody associated to the particular speech. And if you also call it F-note contour. So our objective is whether we can perfectly replicate the F-note contour, the prosody. Specifically for it is very much relevant for singing voice synthesis. Then the SNR ratio, like whether we have, I mean, the generated samples are noise or not, like global variance. So in global variance, when we obtain the male substrate features, then for each of the dimensions, so it is multi-dimensional. So let's say, for example, mostly you two dimension from 24 to 32. For each of the dimension, we try to understand the variance, how it is, the trajectory of the variance. So if the trajectory is very much similar to the synthesized one, then we can say, yeah, in terms of vocal features similarity or male substrate distortion, it has perfectly obtained the features. Now this is the vocoders. So I have already mentioned that these models, the voice conversion models or even the TTS models, are very much dependent on the vocoders that we use. So vocoders can be classified into two categories: statistical and the neural vocoders. So in statistical vocoder, mostly we extract different type of features, not only one. We are dependent on different types of features. like the world vocoder that you can see. It is extracting the F note contour, then periodicity, spectral envelope, and based on that, it is generating the corresponding speech. That's the reason these models are not very robust. So if the vocal features or the content or the model, the speakers for which the model has been trained gets changed for the unseen speaker, unseen content, um, this model does not work very well. That's why we later on we switch to neural vocoder models. So nowadays people mostly use this neural vocoder models, and Hi-Fi is one of the popularly used neural vocoder. So in neural vocoder, mostly the models are based on one specific feature, sometimes embeddings only. Given some intermediate feature embeddings, it can generate the corresponding mail spectrogram, or it can also generate corresponding audio data. The Hi-Fi given the mail spectrogram, it can generate the corresponding audio data. Now, selection of this vocoders also plays a very significant role. Maybe it may happen that the mapping function G, we have trained it very well. Maybe the selection of the function G, whether we have selected any statistical model or maybe a generative AI model like GAN, VAE, or diffusion, we train the model. We train the model very well, such that given a new speech feature representation of the source domain, it can very perfectly convert it to a target domain. However, if my selection of vocoder is not appropriate, then it can distort the generated samples. Then we may think that the mapping function didn't perform well, but it is actually because of the selection of vocoders. Now, selection of vocoder, how we can find? So it is based on the literature survey. So nowadays, say for example, Hi-Fi GAN mostly people are used. There are many different male Hi-Fi GAN is also there that can generate audio data in high sampling rate like 44.1. Mostly the Hi-Fi GAN 22.04 is a sampling rate. Now, based on the literature, what people are mostly are using the vocoder, so we can select one of the prominently used neural vocoder, or maybe we can also design our own neural vocoder. Now, these are the some uh, preceding model. Mostly we used to use the statistical model for this voice conversion. So one was the very popular one is the Gaussian mixture model. So Gaussian, what happens in case of Gaussian mixture model? We assume that the given data distribution is basically a combination of different Gaussians. So given the speech features of X, the source and target domain Y, we first try to find the mean vectors, then the covariance matrix, and then it can see in the left hand side the joint probability. That is the probability of X and Y given the parameter. Now these parameters get updated for based on the different t values. Now once it get trained, given a new x feature, given a new feature from the x domain, the source domain, it try to predict what could be the corresponding feature for y domain, and based on this mean square error, it try to optimize the error. So Gaussian mixture model, as I already mentioned, the Gaussian mixture model. Then we have this phonetic postdoctoral. So these models are not very robust. However, nowadays people are using the hybrid model for different aspects, like this phonetic postdoctoral. So how this phonetic postdoctoral model works, and it is also been, as you can see, it is a hybrid model. In the upper part that you can see that this phonetic postdoctoral information of phonetic postdoctoral has been added with other features just to get the information of phone level information. Now this phonetic from the phonetic postdoctoral we can get at a particular time instant what is the phone associated. Now based on this information, mostly for cross-lingual voice conversion, you use this phonetic postdoctoral with other deep learning model to perfectly convert the feature from one linguistic content to another, mostly for cross-lingual voice conversion. Then we have the vector quantizations. The vector quantization we also use in the field of image processing. So we get the embedding dictionary, the quantized vector from the source domain, and then simply we train a decoder how it can generate from the given embedding the corresponding the target feature, the audio data. So it is a variational autoencoder model. Mostly you use this vector quantization, you use this kind of VAE models. However, people are now in the recent literature, you can see that vector quantization has been incorporated in different other model, like in GAN also, in diffusion also. Now let's jump to the generative adversarial network model. I'm assuming that you are already familiar with the basic mechanism of GAN. Still, I'm just give a brief intro how GAN works and how we can use the mechanism of GAN for voice conversion. So in the diagram above, you can see that we have the domain X and the target domain Y. So initially, the generator tried to map the features from X domain to target domain Y, and we get an intermediate represent Y hat. Now the discriminator, which has already been trained with the real Y, the original Ys, it tried to distinguish between the generator Y hat and the Y. And then when these two features become very similar and indistinguishable, then we say that we have obtained the Nash equilibrium state, because of which the modeler unable to understand, the discriminator is unable to understand whether the generator feature belongs to the real class or fake class. Now this architecture, the mechanism of GAN, we use for voice conversion. Why we jumped from the existing model, the preceding model that I just explained, to GAN? Because of its robustness. However, GAN also have some limitation that I'll tell you, and I've discussed in my latest slide, and then I'll also tell you why we have shifted from GAN to the diffusion models. Now, as I've already explained in my first or second slide, that the first is the feature mapping stage. Now, once the feature are being extracted from the source domain, the converted features, the discriminator try to keeps on distinguishing between the converted and the original one. So once you obtain the Nash equilibrium state, then we simply give the converted features to the vocoder, and vocoder try to reconstruct the audible speech in target feature vocal texture. That's why you can see that the source speaker was the male speaker, the target one, the female speaker. Once the training is done, then the vocoder is capable enough to capable enough to generate the target speaker vocal features given any content of the source speaker. Now, GAN was specifically being used in the field of image style transfer tasks for the process of image style transfer. So then people borrowed it for vocal style transfer, because vocal style transfer and image style transfer is almost similar. The only difference, like, we have the shapes, the geometrical shapes in image and the color distribution, whereas in case of speech features, mostly when you use the male spectrogram MFCC as an input feature, the Forman distribution, the frequency domain distribution, the prosody associated this loudness, etc., basically the distribution of the features and patterns are the formants that gives us an understanding about the content information. So the speaker independent information or speaker dependent. Independent basically means the style of the speaker, and speaker dependent. So speaker independent is the content of the speech, that is formants gives us the information about, and the speaker dependent information, the style of the speaker, both we get from the male spectrogram, and we try to convert the style of the source male spectrogram as that of the target one. So that's why you can associate voice conversion or vocal style transfer to the image style transfer. Now that's why the model that you can see is cycle GAN or star GAN. These are initially been used for image style transfer. Later on, people used, or the researcher has used it for vocal style transfer. This is the working mechanism of the cycle GAN model. Now you have a domain set A and we have a target domain B, and we want that the to convert the generator G A to B. That is the one. I want that the distribution of the color distribution of the domain B get changed as that of the A, and similarly, so it has it has a G A to B and G B to A. So there are two generator. So firstly, what happens? We want the generator to learn how it can change the information from domain A to B. Again, there is another generator which does just the opposite of it, the B to A. So why you do this reconstruction method? We perform this reconstruction method to preserve the geometry of the image. In a similar manner, in image synthesis tasks, we want the content. For voice conversion, we do not want the content to be changed. We want the content to remain what it was uttered by the source speakers. That's why when we reconstruct from B to A, I mean, first we do A to B mapping, then B to A mapping. Then when we get the again reconstructed data or the mail spectrogram, we just try to map whether the content information has been preserved or not. Then we also try to train the discriminator whether it can generate, I mean, whether it can distinguish better between the fake image of domain B and original image of domain B. The similar mechanism that I have explained just my earlier slide. So this is the mechanism of cycle gain VC, exactly same how the cycle gain model works. Just the difference is like the researchers have used it for voice conversion tasks. Now these are some issues and challenges. The mostly the profession generation of high quality nature sound speech is one of the issues that we have. While going through the research survey, we found that even if we generate very high quality speech using GAN models, but there remains some limitation that the generated samples are not in terms of perceptual understanding, the perceptual quality. That is for the mean opinion score, we do not get a very high score. However, nowadays we are the mean opinion score we have obtained is good enough, right? It has crossed around 4.5 something, the highest score considering the 5 benchmark. For the ground truth, if you consider the 5 is the highest score, then for the generated data we are getting more than 4. Then finding the diverse deep learning architecture, which will be the best one for specific tasks, specifically for multiple settings of voice conversion. Then selection of the hyperparameter, then selection of the vocoders that I have already explained. These are the existing issues and challenges. Based on these issues and challenges, we did some contribution to this field of voice conversion. Now, based on the time, I'm just keeping the I'm just giving a brief intro. Otherwise, I'm not going deeper into it. Now, this is one of the work that we have done and got accepted in ICAPS 2023. So FLS GAN VC is a feature specific loss function based self-attending GAN model for non-trivial VC. What we did is it can be seen that in the figure number 24 we have the source domain and target domain, where both the speakers are from different genders. Then we first divided the male spectrogram into different parts. So here the segments we have done is for 3. So initially we have gone through different other segments. Then we found that when we segment it for do 3 segments, then we are getting the best results. Then we use different for each of the segments. We have used separate generators, and once it got generated, we concatenated all together to generate the to obtain the final male spectrogram. Then we also try to try to trace the difference between each of the segments, generated segments, because it is a sequential information. Speech has sequential information. We also want that the sequential information should not get distorted. That's why we use the Siamese laws, which keeps on finding that whether the trace of this sequential information. However, our main contribution was to use the modulation spectral distance. So what was our aspect? I again try to just elaborate, to use the MSD loss and the attention mechanism. But our primary contribution was the MSD loss. So I'd like to explain what was MSD loss. MSD loss was one of the objective evaluation matrices. As I've already mentioned that when we generate some samples, once the training is done, now in the inference stage, when you generate some sample, based on a mean opinion score, we have to evaluate whether the generated samples are very similar to the target one or not. And then we also compare based on the objective evaluation matrix. But we thought that what if we directly incorporate the objective evaluation matrix during training only, because these are nothing but feature specific feature specific objective evaluation matrix. So we can extract the specific features from the generated male spectrogram, the original male spectrogram, and we compare based on by converting it into a loss function. Now, using the objective evaluation matrices as a loss function, we found that during training only we can get a very well trace about how the generated male spectrogram is becoming, whether it is become very similar to target one or not. So that was our main contribution. That so MSD basically, so there's an MCD and MSD, the 2 feature, male spectral distribution and modulation spectral distance. So one extract the global feature distribution, one extract the local feature distribution. So MSD extract the local feature distribution the modulation of the features, how the modulation is getting changed with respect to the time throughout the time. Then we have found that it is the generative sample. For our generative sample, we obtain very low MCD and MSD score. So low MCD and MSD score means higher the similarity, because it is distance metric. Now these are feature distribution. We have in a t-SNE plot. We have obtained that the for our generated model is more closer to the target one with respect to the state of the art. Now I'm not going to the very detail about it. Then we also explored that how we can borrow the matrices we use for image style transfactors. And we can borrow those object evaluation matrices in the field of image synthesis. Now FID, feature insertion distance, is one of the such object evaluation metrics. That is, when we generate some shapes, whether it is facial images or some specific shape, then after generation we can use this feature insertion distance to find the similarity between the or the distortion of whether distortion is present or not based on this FID metric. Now, as because in our generated mail spectrogram also the shapes is basically, or the pattern is basically the format patterns only. Now to understand whether the FID matrix can also work well for tracing the format patterns, we also use this FID metric by borrowing it from the domain of image style transfactors, and we obtain pretty good results. So this is our generator model, and this is the IX is the IX and IY. So I basically the inception V3 model. So this inception V3 model extract the embeddings, and then based on the embeddings we extract the FID score, the feature similarity score, and this score we give as a feedback to the generator. That is, the generator has to reduce its basic objective should be to reduce the FID score such that it can generate more similar main spectrogram as actual to the target one. And then we have also used another relativistic discriminator. So relativistic discriminator, how it works, it basically initially find the L1 distance between the two embeddings, then it does the normalization using the sigma function, and lesser the value, more similar the embeddings are. So there are some other normalization. So we have actually used one combination of normalization method. One is position normalization, and one is a region normalization. So we group two normalization technique in our work. However, this is the most significant work. Contribution of this work was the incorporation of the FID metric, and the earlier work it was the incorporation of the MSD. That means how objective evaluation metrics we can use in voice conversion or speech synthesis model to get a trace about whether the generated spectrograms or the features are similar or not with respect to target one, instead of just relying on the generated samples that we are getting after the inference stage. So these are two contributions we made, and it also got accepted in FCPA. It's a very renowned conference in the field of speech processing. Then we also, so I have already explained how we have used the FID matrix, the FID RPR GAN model for a normal speech to digestive speech to normal speech voice conversion. So given the digestive speech, we can convert into a normal speech. Then is another model that we have introduced. It is for many-to-many voice conversion. So I'm going just to the schematic overview of the many-to-many voice conversion. I've already explained now how the model works. See, the generate G is the mapping function that I've already shown.
Sir, hello.
Yeah.
Sir, how do you convert that diacritic voice to that normal?
Yeah. So
this one.
Yes. Now, say for example, we have a specific content. Say the same content uttered by I explained in the first, initial slide, the same mechanism. We have the one specific content uttered by the normal speaker and the digestive speaker. In the target domain, what we did, we kept the digestive speaker, and the source domain we kept the normal speaker. Now, from the normal speaker, as because we kept the source speaker in the normal target source domain, the normal speaker in the source domain, we can perfectly extract the format information, that is the content related information. But from the didactic speaker vocal features that we can extract from the target speaker, we just superimpose over the content of the normal speaker speech. I hope I make you understand. Means in the source in a source domain, from the source domain, we are extracting the content from the normal speaker, and from a target domain, we are just extracting the vocal feature related information from the direct speaker, and we are superimposing the feature information over the content. So it is like like a data augmentation technique. Exactly not we are exactly we are not generating. We are basically doing the augmentation. That means for the didactic speaker vocal feature, we are augmenting its vocal feature into the over the content of the normal speech. Now this is the one model that we have proposed that got accepted in IEEE Translation Universal Learning System. This GLGAN VC one, it is for many to many voice conversion. So now see, for the it is a generator function, there is a mapping function. So SI is the source speaker, IS source speaker, and CJ is C is basically a class, and J is the jth class, jth speaker from the target domain. Now the generator is generating T hat J. This is a converted feature of the jth speaker, which is similar to the J speaker, and we also have the target speaker actual vocal features. Now the discriminator is extracting the embeddings, and there is we introduce some guided laws. Based on that, it is keeps on finding the similarity between these two embeddings, and it is giving a feedback to the generator based on that. However, there should be another classifier. How this classifier works is, as because we are assuming that the generated feature will be similar to the jth speaker vocal feature, we also have to use some speaker identification model that can identify whether the jth speaker identity we have perfectly extract or not. So it is basically a classification model, speaker identification model. It tried to extract the class or identity of the speaker given the features of the generated features by the generator. So it is doing a classification, and it's also doing a classification, but it is here we have incorporated as a just as a critique. Its basic work is to as a critique to get the similarity between the embeddings and give a feedback. So based on that, we have proposed one specific architecture. So it is available in the internet. You can go to my Google Scholar and you can find this specific model. So I'm also not going into very detail about it. So these are the feature this distribution related measurements. So I have already explained this is global variance, male spectrogram representation, similarity of the male spectrogram. So these things are quite similar as that of any voice conversion evaluation matrices that we mostly use. Then let me go to this this diffusion part, as because is it okay 820. So I'll like to explain the diffusion, because nowadays people have switched from GAN based voice conversion or GAN based speech synthesis to diffusion based speech synthesis, both TTS and for speech to speech. Moreover, nowadays people are also using some hybrid model of GAN and diffusion. So DiffGAN TTS is one of such model. Now how this diffusion model works, so it is quite different from the GAN model. The context is that if you remember the first diagram that I have shown for GAN, we that too specifically for image synthesis task, we have a Gaussian noise, a known unimodal distribution, and we have a target distribution, multimodal distribution, target unknown multimodal distribution, and we have a source unimodal Gaussian distribution. Eventually, the objective of GAN is to convert the unimodal Gaussian distribution as that of the target distribution, multimodal distribution. Whereas diffusion works quite different from GAN, because it takes the data which is already in multimodal distribution, the actual data X naught. Then it keeps on adding some noise. That intensity of the noise keeps on changing based on at the timestamp when exact timestamp t when you are adding the noise. So based on the time instant t, it follows a Markov chain Markov chain of method, based on which it tried to estimate that what will be the future state Gaussian representation of X naught. That is the input data. That is probability of xt given the xt method, given the previous information, what will be the expected representation of the next state. That is what Markov chain works. So at every timestamp, we keeps on adding some noise, and the intensity will keep on changing based on the timestamp. And we take the multimodal distribution of the actual data, real data, to a complete noise, unimodal distribution, a Gaussian noise. Then we again, in the reverse diffusion, this is called forward diffusion. In the reverse diffusion, we try to do the exactly opposite of what we have done in forward diffusion. That is, instead of predicting what xt was given xt minus 1, now our object is to find what was the xt minus 1 given xt. That is, I'm trying to trace the past state, not the future state. And then based on that, I want to estimate, or the model try to estimate, what is the exact noise I have added. That's the reason why I also called it a diffusion process. Denoising process. So in the denoising process, from the noisy representation of the male spectrogram or the data, we keeps on trying to denoise it, and again we want to get the x naught. You can relate it to the variation autoencoder more. Why? In variation autoencoder, we used to give a latent representation of the input data x, and a decoder used to reconstruct the data. So that's why sometimes we call the forward diffusion as the encoding process, and the reverse diffusion a decoding process, because ultimately we're decoding from the noise, complete noise, what was the exact data, and the forward diffusion we're trying to encode the data into a Gaussian representation. Now, why do you do that? Why do you add every time some noise and then give a complete noise representation, then again try to reconstruct the data? Because our main objective here is to find the skeleton, to perfectly approximate the skeleton of the distribution. Maybe not an directly, but using some approximation method. So, but in case of GAN, the problem was like we used to take the help of some discriminator. The discriminator has to be very well trained. We are too much dependent on a discriminator, which is giving us a feedback that whether the data sample is replicating the feature distribution of real data or not. Here we do not exactly have some any intervention of the discriminator. The model itself is sufficiently capable enough to do the reverse and forward and reverse diffusion. And every timestamp, when it is trying to reapproximate what was the noise it added, it basically try to find the perfect estimation of the skeleton of the distribution. Now, this specific model diffusion initially been used for image synthesis tasks. Later, people started, or the researchers of speech synthesis domain started using it for image synthesis. Text to speech synthesis. Now diffusion has also been used for speech to speech, and I will also show that it has also been used for singing for synthesis. Now, GRAD TTS is one of the initial implementation of the diffusion model for text to speech synthesis. Now, see, given the textual transcript hello world, the encoder is encoding the data into latent space, and also it trying to estimate the duration of the words. Now this duration get multiplied with the encoder's information. Now the encoder is having the linguistic information. We also have the duration of the linguistic information. It's simply get added to this. I mean, this information we use this to the embedding, and then see, instead of having one red block, which basically imply one specific embedding, we have 3 copies of it because it has the duration is 3. Now the sky color block have 1 duration. That's why we have 1 copy of it. The green colored embedding had 2 copies because the duration creator has duration as 2. Based on this, we obtain an average male spectrum. Now see, earlier I have explained that we have a forward diffusion process where we get the exact noise, complete noise, and then we do the reverse diffusion. But in GRAD TTS and most of the diffusion based models, TTS models, we do not do the exact diffusion that I have explained here. Rather, we use some prior information. So the researcher have mentioned in their literature that instead of having complete noise, what if we have some prior knowledge information of the textual transcript, and we generate the mail spectrogram based on that, and from the prior information we try to do the denoising part using reverse diffusion and get the exact target mail spectrogram. So once we have this average mail spectrogram, then this xt is a teeth noisy representation of the actual mail spectrogram. Then t is the time instant. So all this information is going to the unit. So it is basically working as a decoder. I've already explained that why you call it a decoder, or because we can relate it more to the variation autoencoder or autoencoder. Then based on this ordinary differential equation solver, we can we can denoise the spectrogram and get the the desired mail spectrogram, which is very similar to the target one. And this is how direct TTS work. Now recently, and the most of the recent SOTA model is the style TTS2, and I too have used is for multilingual TTS to develop multilingual TTS models. Now style TTS was specifically trained for LJ speech and Libri TTS, the English language, considering is the English TTS model. Then we trained this for Hindi language. Now the training for style TTS2, which is diffusion based style diffusion based TTS model, is not that straightforward, because it has some dependency on the prosodic text encoder. So what is a prosodic text encoder? So I have already explained that in TTS we have to give the content-related information in terms of the textual transcript. Then the researchers of style TTS, they have found that instead of giving only the textual transcript, or we are giving the only sentence level information, what if we give the phoneme level information? In that case, the generated samples quality improve a lot. Then what we did is, in order to make it adaptable for Indian languages, we trained the prosodic PL-BART model, prosodic level BART model, PL-BART model for the phone using the phonemes of the Hindi text. The data set we use, we obtain got it from the AI for Bharat official repo. So in AI for Bharat official repo, you can get the data set for different Indian languages. It is publicly available. Also, they have also given the this tokenizer trained for specific languages. We also use the IndicBART tokenizer for tokenization process. For the phonemization, we specific for the Hindi data, we have specifically trained the PL-BART for the using the data of the AI for Bharat for Hindi data. Once we train that, we also train the other models based on the speakers we are considering. The other models has prosodic style encoder, acoustic style encoder, and based on that, the aligner will work. So alignment method I have skipped in my earlier slide. So alignment is very crucial here in TTS. We have to train the model by aligning the textual transcript with the audio, the feature representation that we are getting from the audio data. Unless and until you cannot properly align it, the model will not understand for a specific word embedding, for a text embedding, or phoneme embedding, which is a corresponding feature representation of the mail spectrogram, or maybe any feature representation we take. So the alignment part is very much important. So based on that, we trained our model, and then we did the inferencing. So we didn't change any mod. Our basic objective was just to make it adaptable for Hindi language. So that's why we have just trained the component which has high language dependency and speaker dependency. Thereafter is the inference stage. Now see how diffusion is working here. So this is very important. How diffusion is how we are incorporating diffusion model in TTS. Diffusion as a model to extract feature to map the feature from source to target domain in TTS models. Now, style diffusion is having the information of prosodic text encoder. Prosodic, that is, it is getting the prosody level BART embeddings. It is also getting the prosodic style and the prosodic style encoder information, or the acoustic and the acoustic style encoder information. That is what you are getting from the mail spectrogram. So from the mail spectrogram, it is getting the prosody level information, acoustic style related information, and from the PL bird model, it is getting the phone level information. So these two are related. It is getting from the audio data, and the phone level information is getting from the text data. Now, see, once it is trained with that, in the inference stage, given the style, only the BART embedding that we are getting from the PL BART, from the given the phone as an input, it is approximating what could be the style and procedure embedding. See, earlier the model was getting the information as an input of SP, the proceeding embedding and the acoustic style embedding, as well as prosodic text encoding. Three information it is getting: H BART, SP, and SA. And once it is getting trained, then given a new H BART, it is trying to approximate what would be the corresponding SP and SA. So that is how they train the model for the inference. So it has reduced the time, the inferencing time. So that's why, moreover, the extracted the generated audio data was extremely good. So that's why we thought to use it for our, development for Hindi TTS for specific application, not for research purpose, but for a specific application for Hindi TTS model. Then we also made some contribution to the style TTS diffusion, style TTS to diffusion model. So I would like to show some samples. Okay, just let me know whether you can hear it. Is it audible? Is it audible? My sound?
No.
Okay, let me share again.
Yes, sir, you are audible.
No, I am audible, but my audio, the audio data I am showing.
No, your sound is perfect, sir.
Okay, okay. Can you hear this sound?
No.
Just... can anyone help me, guide me in this? How I can include the sound?
Hello, Dr. Sandipan.
Yeah.
Have you shared the entire screen?
Yeah, I am sharing the entire screen.
Mm.
Also share the audio. Okay, so I'm getting an option. One second. Yeah.
Traveling with the president.
Yes, it's fine.
Yeah. So this is one model. So it is not exactly the style TTS 2 model that I have shown, that we make adaptable for Hindi language. In this specific model, we have made some contribution in terms of speech dynamics, borrowing the basic architecture, but we have made some changes how we can make it adaptable for emotional speech synthesis. So this work we have just submitted in one of the publication. So that's why I cannot show you the whole mathematical representation of the work, how we have done the training and all. Just I'm showing you. Hello.
Yes.
Hello. Yeah. So just
Yes.
I'm showing you the generative samples. So this is the style TTS 2 model. So this is the textual transcripts. You can hear the sound.
There occurred a breach of discipline by some members of the Secret Service who were officially traveling with the president. In Fort Worth, there occurred a breach of discipline by some members of the Secret Service who were officially. In Fort Worth, There occurred a breach of discipline by some members of the Secret Service in Fort Worth. There occurred a breach of discipline by some members of the Secret Service who were officially traveling with the president. In Fort Worth, there occurred a breach of discipline by some.
So what we have found is, if you can minutely hear the sounds, again I'm playing it.
There occurred a breach in Fort Worth. There occurred a breach of.
So in the initial stage, you can see that there's some background noise it is capturing, the style TTS2, and it is more significant in other models. The style TTS2 considering the SOTA, we have found that when mostly when we do speech synthesis for this emotional speech synthesis, when we work with the emotional speech synthesis data, mostly that background noise was coming a lot. So we found that the reason was because the snake activation function we are using. Snake is a very well-known activation function, mostly used for the in the decoder models that we deploy for the speech reconstruction. Now, the basic objective of the snake activation function was like the author said that that we published in Neurix 2020. The author said that when we have a input data which has high periodic information, specifically for signal data, the models cannot work very well when you use the activation functions like ReLU, LU, and other nonlinear activation functions. So for that purpose, we require some activation functions that can perfectly work well for for those data where periodic information is very significant. So based on that, you propose a sinusoidal activation function. But when we found that, I mean, for emotional speech data, the dynamics changes abruptly. The speech dynamic associated to the audio data for a particular time at t, the dynamics of any neutral speech is quite lesser as compared to its dynamics of the emotional speech. So we found that some variation of the sinusoidal activation function, 10 hyperbolic of a learning rate parameter with the sine square of x, that is their actual activation function. We found that learning rate parameter was helping us to change them, I mean, to adapt the model, the dynamics of the speech, to adapt the model dynamics, the variation of the dynamics of the speech, and 10 hyperbolic of alpha of sine square of x plus that existing activation function. And then we found that for I'm just showing you some of the emotional speech demo. Say for example, this is for style TTS.
The 9 the eggs I keep. The 9 the eggs I keep. The 9 the eggs I keep. The 9 the eggs I keep.
This is for angry.
The 9 the eggs I keep.
So from both aspects, what we can see that first of all, the generated sample. See, the generated samples quality is very high, and in terms of MOS. Moreover, the quality of the samples in terms of objective evaluation matrices was very high. So when we compare with oscillator TTS and style TTS2, we have also mentioned that style TTS2 itself, their MOS, their objective evaluation scores are quite high. We just make how we can change the style TTS2 architecture to make it adaptable for emotional speech. However, the style TTS2 data itself is very, in terms of MOS, the score is very high. Next, let me go to the next part. This is called singing voice synthesis. Now, singing voice synthesis is presently the work, I mean, the project with which I am associated in digital audio processing lab for IIT Bombay. Before I'm jumping directly to the model, let me tell you how TTS and singing voice synthesis is different. So this is another presentation. So I am unfortunately I'm unable to share directly this PPT. So that's why I'm sharing the just to make you understand how singing voice synthesis is quite different from the TTS, exact TTS. I hope my this specific screen is also visible. PPT is also visible. Okay. Now see, in case of singing voice synthesis, unlike TTS where we only have the textual transcript, here we have the lyrics. Lyrics is the very textual transcript, but we also have the music score. What is the music score? Let me come to the music score part. And I also mentioned how we are, I mean, from what aspect we are trying to make changes to this specific model. Now see, let me zoom in. Okay. So this is the interface of Pratt. The screenshot I have just included here. Now see, this is the textual transcript. Hum tere bin ab reh nahi sakte. So this is a textual, normal textual thing. Now, what if we would have just taken the textual transcript for DTS? Then there we do not need to deal with high modulation, the prosody, the melody, and notes, etc. We can simply use the text, or maybe you can extract the phones, and then we can train child DTS to any existing model. But when it was a specific song of Arijit Singh, and we wanted to make it derivative, the existing deep singer model, I'll show you the deep singer model. So deep singer model and most of the diffusion-based singing voice synthesis models are trained for opera data, opera music data, and that too opera of Chinese, Mandarin, and Western music. For Indian music, that too is for classical music. I mean, there is no available open source data for classical and for Hindi or any other Indian languages for singing voice synthesis tasks. We do not have, as of now, the open source data. So that's why we extracted some data online available where we do not have the copyright violation problem. Then we use some data from available in the internet for Hindi classical language, Hindi classical music and Bollywood music. Then we found that when we have this lyrical context and we are extracting the syllables, the phones, as well as the duration associated with the phones and the words, we also have to give the notes. Definitely, you must. It is called the music score. I mean, in music score, we have the lyrical content, syllable content, and duration associated to words, syllables, as well as the notes associated to each of the particular content or the scales. You can think of like a scale. Then we found that for Indian classical, training the model for alignment, because I have already mentioned that for TTS or singing voices, whatever we do, we have to align the data, what text data with respect to the audio data. Otherwise, the model won't understand which text belongs to which part of the audio. While doing so, we found that there are some problems which we were facing for aligning. First of all, the recognizing the phones. Now, see, when we observe the Indian classical music, we found that in intermediate parts there are some phones or syllables appear for long time instance. Say for example, the ni pa re. So this re is coming for a long time interval. However, for TTS, if we have just a textual transcript and taking the example of Ragiman, Piya ki. So if it is normal text, then we can simply like Piya ki nazariya. But if it is a song and it is a lyric and we have a prosody associated with melody associated with note associated with, then it is becoming Piya ki. Now this key, the model, the speech recognition model was unable to detect. So it was just detecting the first time it was uttering. Next time onwards, it was simply giving that the is basically the silent. The long vowel, it was detecting as silence. Moreover, we found that the bandish, the classical bandish for different classical gharana changes for the same raga. Maybe the ragiman for Bhatkhande gharana will be different from Jaunpuri or maybe from Vishnupuri gharana. So that way we found that gharana wise also the basic structure of the raga get changed. The transitions also get changed, and transition also depends on the singer we are choosing. So the singers in classical, the classical singer has a lot of freedom, so they can make they can create their notes, or they can make modification to the existing note based on their experience, just following some rules, but based on their experience, they can make changes. Now, these models are quite for a specific for a specific content, for a specific raga, for a specific musical composition. It has lot of freedom, and this freedom depends on the specific singer we are choosing. That's why it became quite complicated for us how we can train our model. Either we have to make it very much uh, speaker dependent, sorry, the singer dependent. At the same time, how we can detect the long utterances. Then we use some concept of onset detection. That is the transition. So we found that whenever this is a transition from vowel to consonant, and sometimes to detect the long utterance, whether it is silent or not, we can also take the help of voiced unvoiced recognition models. Now, say for example, if a model can perfectly recognize voiced and unvoiced parts or silent and non-silent part, then if a recognition model uh, wrongly misclassify one uh, phone as a silent, then we can simply take the help of that silent and non-silent detection model to find whether actually the phone belongs to silent part or not. That way, we again try to fix this issue. Then we train the model as of now just for one single speaker. Now we are trying to make it adaptable for different singers, because I have already told you that based on the singers, suggestion of singers, the rules, the musical compositions for the same musical composition, the transitions get changed. There's a very lot of variation, which is not present, in case of opera music of Chinese Mandarin, I mean Chinese Mandarin opera, or maybe Eastern classical. So Western classical are very straightforward, but Indian classical or Indian Bollywood music, the transitions are not that straightforward. So this is what we found the issue. Then we try to modify the existing state of the art model, state of the art singing voice in this model, the deep singer model. I'm again coming to the deep singer. So this is a diffusion-based singing voice in this total diffusion-based singing voice in this model. So I'm running out of time, so I will not explain much about it. So it is having the similar way. You have the X as an input. So X is basically the music score instead of directly instead of only having the textual transcript, having the music score. Now the encoder is giving this extracted music score to denoiser, as well as the step embedding, and also the noisy middle spectrogram. Based on that, it is trying to reconstruct the audio. And then there's a shallow diffusion. The shallow diffusion also I'm not explaining over here because I am running out of time. So I'm just explaining how we make it adaptable for a new language, specifically for Hindi. So we used Hindi phone recognition model. This is X-phone model, then IndicBARD model for extract the embeddings for text, Hindi text. Then also you used for syllable, Hindi syllable recognition model. So from all these models, we just extracted the embeddings. We added the fused embeddings to it. Thereafter, you use different types of loss function in order to extract the perceptual loss, in order to extract the musical information related loss, in order to extract the prosody related loss, because all these things very much important in context of this singing voice synthesis. However, in this existing model, they have not used so many variation of losses and fused features, because they have specifically trained it for one specific language based song and one specific singer. And as I have already explained that for opera, Chinese opera or Western classical opera, the transitions are not that complicated as that compared to the classical. So we wanted to make it adaptable for classical. That's why we use different type of embedding, feature embedding, loss functions to make it adaptable for a specific language and specific style, speaker style, by training it for using some pre-trained model and also training for some specific for our existing singers. Then this is called audiovisual voice conversion. So in audiovisual, as the name indicates, that instead of just having the audio data, we also extract the visual features, and then we condition the decoder that given the embeddings of the audio and given the embeddings of the visual feature, how it can generate the corresponding frame level information in the video, and how the leap also gets synced based on that. So there is a leap singer model, diffusion based. I forgot the name. EMD diffusion, where they have trained it for this audiovisual syncing as well as synthesize. audiovisual synthesis and syncing and synthesize. Then we also have this human computer interface based speech synthesis model. So where we use these brain signals, we can extract this different EEG signal, alpha, beta, gamma, delta, theta, and we can convert it into spectrogram representation. Then we can also get the corresponding content-related information for a specific subject, and then we can train. So it is like training the model. Instead of having the textual transcript, we use the embeddings, the feature information that we are getting from the EEG data. Now I will also show one just small video where some researchers from University of California, San Francisco, they use a data, they train it, they prepare a data set, train the data set for this specific task. And this is my last slide. After that, it is finished. So I'm just finishing with my last content. This one. Okay. This. Now see how they have trained the model. Initially, they asked the subject to think for a specific content. Based on that, they extracted the brain signals. So they know what was the content. They also know the corresponding brain signals. So this is the information which is very much required to make the model align. That make the data align. There's two data. There is the EEG signal or the brain signals and the textual transcript. The way we require for TTS and also singing word synthesis. Thereafter, once the model get trained, so they are showing here in real time how it. Now see here the subjects, she is actually unable to speak. Now she is thinking something and the model is generating then and then the corresponding speech. So this is a very recent work on and very recent development on speech synthesis, the domain of speech synthesis. Recently means just 1 or 2 years back, people started working on that. Now different companies are investing a lot of money for brain signal to image synthesis. How that you can make it adaptable for those speakers who cannot speak. Actually, the people who cannot speak, they are unable to speak. So there is very creative domain and advancement of this domain of speech synthesis. Okay, thank you. Here I am ends my talk. If you have any question, then you can let me know. If anyone have any question, then I'll be happy to.
Sandipan, I have a question.
Yeah.
Actually, Dr. Sandipan, in the last video, you have shown that they are gathering some EEG signal, I think, right?
Yes.
Is it not very man-to-man? What do you think?
It is very so. One is it is subject specific. Another thing, there are some noises also associated with it. So I'm exactly do not know how they have deal with these things because I specifically worked on the EEG signal classification during my PhD for some additional projects, and I faced this issue that sometimes some specific, because see, when you take the EEG signal, there are different frequency, alpha, beta, gamma, delta, theta. Now these variations for a specific subject depends. I mean, it is very subjective. Means for some subjects, some of the signals get changed for a specific sentiment. We do not see the exact variation to another subject. Now, maybe if you can increase the data, you can observe this variation in a more appropriate manner. However, when we also face this issue, so we have to use some pre-processing technique to use the frequency up to a certain level, given some threshold. Apart from that, some noises, noisy data was there, or the data set we have used. So I do not know exactly how they have prepared the data, whether it is very subject specific and how we can make it adaptable for different subjects. Because I exactly do not know work on this human-computer interface based speech synthesis. But yes, it is a very valid issue. I believe so.
And what about your view on diffusion models?
Diffusion model. Huh.
What is the future of diffusion model?
So as of now, see, based on the comparative analysis, if I see based on the comparative analysis, we have found that diffusion works. I mean, the generated samples are far better than the only if you use only the GAN model, so the solo GAN model. But when you do
Yes,
hybrid model like DiffGAN TTS, now DiffGAN TTS shows that when we combine the concept of adversarial learning with diffusion model, that the generated quality get improved. Now the style TTS2 model, I'm just going to the style TTS2 part in my slide. Now, style TTS also use this adversarial learning mechanism. See, GAN is basically a mechanism. Instead of saying that exactly a model, it is basically a mechanism, adversarial learning mechanism. Now, the people of style TTS2 also, they have also used this adversarial learning mechanism. See, here you can see that I don't know whether can you see my cursor? So that synthesized
yes.
word waveform is also going through another means LLM model, SLM model. Then there is a discriminating head that is trying to distinguish whether it belongs to real class or fake. That means they also use the learning mechanism, adversarial learning mechanism to style TTS2. And style TTS2 one of the best existing style TTS model for especially for English language. Now we can say that so that maybe GAN itself means if you use only the GAN model for TTS or voice conversion may not be it is very useful, but if you combine GAN, diffusion, or maybe like I have shown the phonetic posterogram or vector quantization, different model, hybrid model. So now hybrid model can improve the existing models accuracy or maybe the generation quality far more. Only relying on specific model, maybe this combination can help us. So if you ask me what is the future of the diffusion model, at least I'll say that the combination of diffusion with different other learning mechanism or different other existing models may give us a very good result. But I don't know in future whether we will get a very better generative model as such, like as you have like diffusion. Definitely we
Okay,
have,
fantastic.
but as of now, not have.
Thank you.
Thank you.
Participants, if you have any other doubt, you can go ahead with your queries. Okay, so I don't think there is any question.
Okay,
So, so thank you, Dr. Sandipan, for your nice explanation on speech synthesis from classical approaches to the state-of-the-art techniques. And then you have also discussed how we are going for the singing voice conversion. So that is also very, I think, new. I think